For section 10.5, we're going to be moving on to the second type of bonding that we're going to be discussing. So just as a reminder or as a review, the last type of bond that we discussed was ionic bonds. So ionic bonds form between a metal and a nonmetal. Okay, they're going to transfer electrons in order to become charged ions. So one's going to be positive, one's going to be negative, and then that's what's actually going to make the bond. The fact that they are opposites, they're going to attract to each other just like a magnet, and that's what creates the ionic bond. Okay, it's a very strong bond, we'll come to find out. Okay, covalent bonds are different, almost completely different than the ionic bonds. So for covalent bonds, they're usually formed between nonmetals, so a nonmetal and a nonmetal. Okay, they share electrons instead of transferring them, and then they form molecules. So a molecule is just atoms that are joined by a covalent bond. Okay, we found that with ionic bonds, we actually form compounds. Okay, whereas with covalent bonds, we form molecules. Okay, and then just as a reminder, just like our metals, all nonmetals want 8 valence electrons except for hydrogen that only needs 2 to have a full shell. Okay, so remember we talked about all atoms want to have 8 valence electrons in their outermost shell to be happy, and the only exception to that is hydrogen. It only wants to have 2. Okay, so if we look at the different diagrams here, we have the different elements combining together in order to form these covalent bonds. Okay, so hydrogen, oxygen, nitrogen, and carbon, they all are classified as nonmetals. So because it's nonmetal to nonmetal, it is a covalent bond. Okay, and so what happens is you see that oxygen has 2 unpaired electrons. Here's an electron that's unpaired, and here's an electron that's unpaired. So it needs 2 additional electrons in order to be happy and have 8 in its outer shell. Okay, you'll notice that hydrogen has 1 electron, this one has 1 electron. Remember that for it to be happy or to be full, it needs 2. So it has 1 unpaired electron and 1 unpaired electron. So it wants 1 electron. And this one wants 1 electron. So what happens in the covalent bond, instead of transferring the electron to the oxygen or the oxygen transferring this to hydrogen, they share. So these 2 electrons, this one and this one, are going to pair up. Okay, and then this one and this one are going to pair up. And so we see that these 2 electrons are being shared between this oxygen and this hydrogen. Okay, and then these 2 electrons are being shared between the oxygen and this hydrogen. Okay, so the water molecule actually has 2 single covalent bonds. Okay, so 1 pair equals 1 covalent bond. Okay, so we see the same thing here with nitrogen. It actually has 3 unpaired electrons, so each of the hydrogen are going to kind of pair up with each of the unpaired. Okay, so that we get a shared pair between this hydrogen and nitrogen. We get a shared pair here and a shared pair here with the different types of hydrogen. Okay, so ammonium with the nitrogen and hydrogens actually has 3 covalent bonds that are singly bound together. Okay, so they have a single pair of electrons that are being shared between these 2 elements. Okay, one thing I do want to note is that you do see that they still have the paired electrons. Those paired electrons are not being shared. Those are just part of the atom. Okay, so for in this case, these are the electrons that are only on the oxygen, and then this pair of electron is only for the nitrogen. Okay, they're not being shared. All right, if we look at oxygen and oxygen pairing together, you'll notice that this oxygen has 2 unpaired electrons. Okay, same thing with this oxygen. It has 2 unpaired. Okay, so they kind of fit together like a puzzle piece. So this one will pair with this one will pair with this one. Okay, so we notice that they're actually sharing 4 electrons. They have 1 pair and 2 pairs. Okay, so an oxygen molecule actually has 1 double bond. Okay, And so we generally see these with like stick figures. And so it would look kind of like an equal sign where we'd have our O and then two lines and then an O. Okay, so each line represents a pair of shared electrons. So in this case, there's two pairs, a total of four. So it's a double bond. Okay, we see the same thing happening with oxygen and carbon. Okay, the carbon is going to pair up with two of the oxygen's unpaired electron and then does the same with this other one with its other two electrons. Okay, so each oxygen and carbon, okay, and then carbon and this oxygen have two pairs of shared electrons, right? A total of four. So here, if we drew our lines that kind of connected the dots between the two, we would have those equal signs again. So a 0 or our O, the two lines that represent the two pairs of electrons, we'd have carbon, again the two lines, and then oxygen. So CO2 has two double bonds, okay, because each of these are a double bond. All right, nitrogen, you'll notice, has three unpaired electrons, and again it's going to kind of fit together like a puzzle piece, kind of like the oxygens. So this unpaired is going to match with this one will match with this one, and then this one will match with this one, okay? And so when we kind of line them up and box in all of the shared electrons, you'll notice we have 1, 2, 3 pairs. So if we were going to be drawing it in stick form, we would have a line here representing one pair, a line here, and then a line here. So 3 lines connecting these two nitrogen atoms. And so nitrogen has a single triple bond. Okay, there's no such thing as a quadruple bond, just so that you're aware. So we're going to talk about electronegativity. So some atoms can attract electrons with different intensities, and we can use the electromagnetic scale in order to help us determine how strong an atom is at holding on to electrons, okay? So think of it as strength. So some of the atoms are going to be like bodybuilders, basically. So they have a lot of strength, and if it was a tug of war, they're going to be more likely to be able to pull the rope towards them, or in this case with electrons, going to pull the electrons toward them more often, so the electron actually spends more time with the one with greater strength, the greater electromagnetivity, than the one that has a weaker electronegativity. So this causes different atoms to share electrons unequally. So when we have unequal sharing, it's actually a polar bond. Okay, whereas when we have equal sharing, it's nonpolar. Okay, so in terms of polar, if we like our Earth is polar in that it has a north and a south side, okay, to it at the poles of the Earth, okay, that is positive and negative, okay. So that's what we're going to see, is that there's going to be a positive side and a negative side to these molecules. So on the cheat sheet that you guys picked up for today, or that I attached to this assignment, the top portion just lets you know, or just tells, kind of breaks down our metals, the staircase, which are metalloids, which separates our metals and nonmetals, and then all the grayed in section is our nonmetals, okay? So for like covalent bonding, we would need 2 of the gray boxes combined together to be covalent. If it's ionic, we would need a white box and a gray box bound together, because then it would be a metal and a non-metal together to make ionic, okay? Also, at the bottom of that cheat sheet, there is this and this available to you, okay? So all these numbers are the strength of the electronegativity of the atom, okay? So you'll notice that fluorine is the strongest at holding on to electrons, whereas like francium is the weakest with 0.7. Okay, so what we can do is we can determine the type of bond that is occurring in a covalent bond, whether it's nonpolar or polar, based on the difference in their electronegativity. So we would take the two numbers and subtract them and determine if they fall in this range, 0 to 0.4, which is a nonpolar covalent bond, or from 0.5 to 1.9, which would be a polar covalent bond. Okay, we find that if the difference is above 1.9, then that just means that one of the atoms is just so strong that instead of sharing the electron, it just full on takes the electron. And in that case, it would be an ionic bond. Okay, they're no longer sharing the electrons, they're actually transferring electrons. Okay, so for example, if we were going to combine fluorine and nitrogen, we would subtract. So fluorine has an electronegativity of 4, nitrogen has an electronegativity of 3, so 4 minus 3 would give us 1. It would be in this range between 0.5 and 1.9, so it would be considered a polar covalent bond. So whether the molecule is polar or nonpolar has to do with the shape of the molecule and the balance of charge. We're not going to spend a lot of time on this. I just want to kind of bring it up. But shape has a big thing to do with if a full molecule will be polar or nonpolar. Okay, it kind of has more to do with organic chemistry. So we won't spend much time on it, but just know that that does cause a difference. So when the covalent bond is polar, there's a more positive end and a more negative end. Okay, so we get a partially positive end and a partially negative end because the electron is spending more time near the stronger atom than the weaker atom. Okay, so the weaker atom is going to have a more positive charge, whereas the stronger one, because it can pull on that negatively charged electron, is going to have more of a negative charge. Okay, so this causes the molecules to interact with each other. So water is a perfect example of this. Water has kind of a bent shape, kind of like a triangular shape if you've ever seen a molecule drawn out of water, where you kind of have oxygen and then you have hydrogen and a hydrogen attached to it. Okay, so hydrogen actually has an electronegativity of 2.1. You'll notice that oxygen has an electronegativity of 3.5. So if we subtract those, it would be 1.4. So it does fall in the range of being polar. Okay, where oxygen is the stronger of the two. So what we find is that the oxygen end of the water molecule has a more negative charge, whereas the hydrogen end has more of a positive charge. And so what happens is that the water molecules can kind of interact with each other, where the positive and negative ends kind of line up together and kind of stick to each other. So it's not a true bond. It's not a very, very strong bond, but it does allow water to do some very interesting things. Okay, two of the things that water can do is that it has the property of adhesion and cohesion. Okay, so adhesion, if you look out the window, if it's raining today, it might be raining. I think it is supposed to be raining. You'll see that there are water droplets on the window, on the window pane, on the glass. Okay, and so they're kind of defying gravity being on the glass. And so you probably never thought of it before, but it is kind of defying gravity. So the reason that the water molecules can stick to the glass and make water droplets is because they have this property of adhesion. Because they have the slightly negative and slightly positive side ends, it causes them to be able to stick to other surfaces. Okay, cohesion means that the water molecules are attracted to itself. Okay, this is what actually gives water its special properties, such as making water droplets. Okay, you know how it kind of balls up on itself, and also surface tension. Okay, so if you've ever seen like those little like skitter bugs, though, like water bugs that can walk across the water, okay, they're able to do that because of cohesion. It causes surface tension on the water, so very, very light things like a leaf falling on a pond isn't going to automatically sink because of those bonds that are created on the surface of the water. Right? And so we're actually going to do an activity tomorrow having to do with cohesion, where we're going to kind of explore that further.